Hello, good morning everyone. Today, inshallah, we will start our session. In this session, I will talk about the implicit function theory, the directed derivative, the tangent plan, and extrema in multivariable functions. This session is really very important, and it is the start of the new topics that you will face in the second midterm, inshallah. I want you to go through it. I have solved plenty of problems for you, so you can solve them all. And please, I want you to use your pen as much as possible and try to solve as much problems as possible. I believe I sent you the PDF for this lecture 2 days ago or 3 days ago, something like this. So please go through it and try to solve, as I told you, as much as possible from the problems in exercises and the previous exams. I will start with the implicit function, which abbreviation is IFT. The implicit function theorem is a powerful result in multivariable calculus because I can get one of the variables as a function in the other variable. If I can do this, then it's gonna be great. So if you have a function with y and x, for example, as you would see from the coming slides, and you can separate y by itself as a function in x, in this manner, your function is an implicit function. So once more, it's really very important in multivariable calculus that tells us when an equation involving multiple variables, as I told you, can be solved for one of them in terms of the other, even if we can't solve it explicitly. And another consequence for this theory is I can get the derivative of this variable with respect to another variable using the theorem of the implicit function theory, as I told you. So if I have, number one, a function f of xy equal to 0, those are the main two conditions that will help me out to find the or to apply the implicit function theory and to get the derivative of one variable as a function in the other. So the first condition is you can find that the value of the function at certain point or the point in interest is equal to 0. So once you substitute in your function by x node, y node, you will find the values equal to 0. Step number 2, or the second condition that must exist, is that the derivative of f with respect to y at the concerned point shouldn't be null or shouldn't equal to 0, as you can see. So mainly, then there exists a function y f of x, which I can write as f of x and f of x. If you remark, the main idea, I can get y as a function in x in this form. And the most important thing, or the biggest advantage, that is that I can get the derivative of y with respect to x, of y with respect to x, okay, simply by dy by dx equal to negative f sub x over f sub y. So once more, if my function or the variables that I have leads to or apply to the implicit function theory, I can get the derivative of one of them as a function in the other simply by first of all confirming these two conditions. Then the derivative of y with respect to x will equal to minus f sub x divided by f sub y. So I will get the partial derivatives, then I will divide them on each other, and finally I will substitute at the point x node, y node, as you can see. And that's mainly the main theory of the implicit, as I told you. This is the derivative of f with respect to x, and derivative of f with respect to y. Don't forget the negative sign, as you can see. If I want to apply this on this problem, it's going to be really very easy. All I have to do is to follow the steps that we have, step by step, and then finally you will be able to reach the results that I told you about. So first of all, I will need to evaluate the derivative of y with respect to x for this function, which is y squared minus x4 equal to 0. So all I specifically at the point -1 and +1. So first of all, I will need to check the value of the function y squared minus x to the power of 4 at this point. So simply, all I have to do is to give this a check. So first of all, I will try to substitute by the two values. Of course, this is the consequence, as I told you. So number one, I will try to substitute, replace y by 1. So I will have, that's the first thing to check, getting f at -1 and +1, which leads to, it's going to be 1 to the power of 2 minus -1 to the power of 4, which result to 0. So that's the first check. The second check, I will get f sub y. So for this function, I will have f sub x and f sub y. If you differentiate with respect to x, it's going to be -4x to the power of 3. If I differentiate with respect to y, it's going to be a 2 over y. Remark that the value of the function of the derivative with respect to y at the indicated point doesn't equal to 0. So once you substitute, you will have 2 times 1, which is 2, not equal to 0. So I can apply the theory of the implicit function theory as I was telling you. So this is at the point -1 and 1. Since f sub y is equal to 2y, so once you substitute y by 1, it's going to be 2, doesn't equal to 0. The theorem can be applied, and the result is really very simple. All I have to do is to just get dy by dx, which is equal to negative the partial derivative of f with respect to x divided by the partial derivative of f subject with respect to y. So all I have to do is to divide -4x cubed by 2y and with a negative sign. That's the application. Then I will substitute by the values at the point, which is -1 and +1, and hence I will have the value of the derivative of dy by dx at the required point, which is -1 and +1, as you can see. This is really very important theory. As I told you, it gives you the ability to find the derivative of the function at the indicated point, as you can see. So once more, if I want to find the derivative, all I have to do is just to substitute, as you can see. In higher dimensions, okay, if I'm talking about higher dimensions than R1, like Rn plus m into Rm or something like this, and also still I have the function that's equal to 0, and x belongs to Rn, y belongs to Rm, if f is continuous, differentiable, and the value as x node, y node is equal to 0 or at the point in concern, and the partial derivative with respect to the value is also doesn't become to 0 level, I can find the following. I can find the Jacobian, which stands for the derivative of the function with respect to y. Okay, so get the Jacobian matrix of the derivatives with respect to y. That's the Jacobian of f at y with x node, y node. And be sure that it is invertible, which means it doesn't equal, it's not singular, it doesn't equal to 0. So it is invertible, and hence get the Jacobian with respect to the other variable. Once the check is okay, I can find the derivative really, very simple by getting the Jacobian derivative with respect to x divided by, but in matrices, we don't have division. This is why we multiply by the Jacobian of f with respect to y to the power of -1, which is like division exactly, but in matrices. This theory gives you the ability to find the partial derivative of a function or with a variable with respect to another variable, partially if you have more than one variable. I will shortly give you an equation, an example on the application of this theory, especially in 3 dimension, as you will see. In this version, it's exactly like the versions, like the slides that we did go through it. It's exactly the same. So if you have f and it's mapping from R2 into R, such that f of xy is equal to 0, and if you have the 2 points or the point A and B, and it is defined on the domain and the neighborhood, and you have f of xy equal to 0 at this point. So as a result, f of AB equal to 0, and the partial derivative with respect to y doesn't equal to 0. In this manner, we can get the derivative of the function with respect, or the total derivative of the function with respect to dy by dx, as I told you, simply by getting negative partial f, partial x, partial f, partial y at the indicated point, which is exactly the same like what we did. So, for example, for this problem, which is x squared plus xy plus y squared negative 3 equal to 0, we want to know if this equation defines y as a function in x and also at the point 1 and 1, and also I need to compute dy by dx. As I told you, it's difficult to separate or getting y as a function in x, so all I have to do is to try to apply the implicit function theory, as you would see. So the first step in doing this, I will try to check the value of the function at the indicated point, which is 1 and 1. So simply, all I have to do is to make the substitution. It's going to be 1 to the power of 2 plus 1 minus 3. If you add those is going to be 3 minus 3, so it's going to be equal to 0. So those mainly the two checks that I'm going to do. The first of them is to substitute in your function by x node, y node, which is 1 and 1. And this is, as you can see, I will start substituting. So it's going to be 1 to the power of 2, 1 times 1, 1 to the power of 2 minus 3. The result is equal to 0, which means the first condition is okay. I will go to the second condition, which means I will get the partial derivative of f with respect to y. Once you get the partial derivative of f with respect to y, which is really very simple. So if I want to get partial f, partial y, it's going to be really very simple. Differentiating with respect to y, it's going to be x, then differentiate with respect to y, it's going to be a 2 over y. At the point 1 and 1, it's going to equal to 3, which means it doesn't equal to 0, and so I can apply. So once more, that's the derivative, as you can see, x plus 2y. Start substituting by 1 and 1, and the value is 3 doesn't equal to 0. The two conditions are satisfied at the time being, so simply I can get dy by dx. Once more, I want you to remember that dy by dx is equal to negative f sub x over f sub y. Really very simple and easy to get. So once more, the implicit function there states that y can be written as a differential of y of x. So all I have to do is to get the derivative with respect to x, which is 2x and y. Get the derivative with respect to y, which is x plus 2y. Divide them on each other. That's the result. Then apply, instead of x and y, by the value of the point 1 and 1, and then you will find the value of your derivative, as you can see. So that's a huge advantage of the implicit function theory. In a similar manner, by the idea, there is another way I can use to get y dash from this function, which usually I used to give this to your companions previously. Although it's not stated in our slides, but also it's really very successful way in order to get y dash. It's really very simple. All I have to do is to forget about f and start differentiating this function as x, as y as a function in x. So if I start differentiating x squared, it's gonna be a 2 over x. Then I will hit x and y. These are two functions multiplied in each other. So I will bring the derivative of the first function times the second, plus the derivative of the second function times the first function. So it's gonna be simply the differentiation of x, which is equal to 1 times y plus x will remain times derivative of y, which is y dash. Then plus I will start differentiating y square, which is gonna be simply 2y y dash, and all of it is equal to 0. If you look to this form, now I can take y dash as a common from the third and fourth terms, and then it's trying to separate y dash on one side. So simply what I mean is taking y dash as a common, so I will have x plus 2y times y dash on the right hand side, on the left hand side. I will move 2x plus y, these two terms, to the other side, so it's gonna be a negative of a 2x plus y. Then I will divide, so y dash, which is dy by dx, simply will be a negative of a 2x plus y divided by x plus 2y, as you can see. The same result exactly. So if you look at this guy and you look to that guy, they are exactly the two results. So once more, I can either using the theory of the implicit function or doing the implicit function derivative. This is what I mean by, similarly we can do this by this way, just differentiating the function with respect to x. Y is a function in x. I will have y dash, as you can see. I will rearrange my equation, and once more you will have, as I told you, 2x plus y, 2x plus y, the negative sign really exists, x plus 2y in the denominator, and as you can see, I had the derivative of the function in front of me. This is also a very successful method in order to get the derivative of your function, as you can see. So that's about the implicit function theory, f from R2, as you can see. The definition can be extended. Instead from R2 into R, I can deal with it from R3 into R also. And this is a generalization of what we did go through in the previous slide. So at the neighborhood of the point AB, where and the W of C such that V cross W belongs is a set of U, I will have the functions equal to 0, and the condition that the partial derivative with respect to Z doesn't, that's the first one, that the value of the function is equal to 0, and the derivative of f with respect to the variables that I want to separate, partial and partial Z, doesn't equal to 0. I can write now, that's the second condition, and according to the definition, then I will have Z as a function. I can separate Z as a function in x, y, and that's we can find Z as a function, which is the meaning of implicit, and I can find partial Z, partial x, partial Z, partial y, as you can see. I can find partial Z, partial x, and the partial Z, partial y, which is going to equal to partial f, partial x, partial f, partial z, and as I told you, with respect to y. An example on this problem is, will come to you in this problem, or in this example. Want you to consider the surface f of x, y, and z, which is x squared y squared plus z squared minus 9 equal to 0. It's an equation of a sphere. Remark that I should have my equation equal to 0. Then I will check. He needs you to find the partial derivatives at the point 2, 1, 2. At the point 2, 1, 2. So all I have to do is to check first that the point 2, 1, 2 belongs to the function, which means if you make a substitution, the value of the function will equal to 0. Then I will need to check the partial derivative of this function with respect to z at the indicated point is not equal to 0, because I will divide on it down the road, as you will see. So the first step I will need to check is to start substituting by 2, 1, 2 in the main function and see how it's gonna be. It's gonna be 2 to the power of 2, 1 to the power of 2, 2 to the power of 2. The sum of them is positive 9 minus 9 is equal to 0. So the point belongs to the surface first of all. The second check I will need to get the derivative of f with respect to z. It's as crystal clear as you can see. So I will differentiate this function with respect to z, which is gonna be 2z. Okay, replace z by the z component in the point, which is gonna equal to 2. The result is 4 and not equal to 0, which means I can apply the implicit function theory and define the partial derivatives of z with respect to x and of z with respect to y. Before doing so, I will differentiate my function with respect to x, with respect to y, and with respect to z. This is what I'm going to do at the time being. So, first of all, I will try to get the partial derivatives, partial f partial x, partial f partial y, partial f partial z. Then I can get simply the derivative of partial z partial x, which is partial f partial x divided by partial f partial z. It's gonna be 2x over 2z with a negative sign. And in a similar manner, for partial z partial y, it's gonna be negative, differentiating f first with respect to y, then dividing by partial f partial z, as you can see, and that's the results that we have. The derivative of x, of z with respect to x, the derivative of z with respect to y, which is -1 and the -half, as you can see. That's a huge advantage from the implicit function theory. Okay, once more, I will talk about the second topic, or I want to talk about the second topic, which is really very important in this session, which is the directional derivative formula. This is one of the important topics in the multivariable calculus in general, because it helps you to identify the value of the function in a direction of one of the vectors. So I can find the derivative of the function with respect to x, which is a special case from the directional derivative. I can find partial f partial y, which is also another special case from the directional derivative, and also I can find the derivative of the function at certain point in the direction of any vector I can choose. What's going to help me with this is the directed derivative formula, which is really very simple. Once your function is differentiable, all I have to do is to follow this law. I will bring the gradient vector of the function at x and y, then dot product the direction or the vector, but I will be sure that this vector to be on a unit vector form. What's the unit vector for? It means that the magnitude of the vector that I'm going to use is equal to +1. I will go through it with you in shortly in an example in details. So, in more details, the point xy is where we are standing, the location at which you want to measure how the function is changing is w. So all I have to do is to get the directional derivative, which is the derivative of f at the point x naught y naught, but in the direction of w. That will give me the rate of change of xy at the direction of the indicated vector. xy specific location, w in the direction that I need to evaluate the derivative at, and dw is the rate of a change of the function in this direction, as you will see. The previous directed formula will be used in case of functions is differentiable. I can use the previous relation, which is once more the directed derivative of f at certain direction is simply the gradient vector of f times w, and this is unit vector. This is gonna be, you will be able to do this once your function is differentiable, and you can get the partial derivatives, of course. If not, if I'm dealing with a piecewise function or with a function that's not differentiable at that point, or I'm suspecting the differentiability, I will use this law, which states the directed derivative of f at the point x naught y naught in the direction of v. It's going to be very, very simple. It's the limit of h tends to 0. Remark, x naught plus h times a and y naught plus h times b minus f of x naught y naught divided by h. Those parts of an a and b are the coordinates of the vector v, which is multiplied by h. So once more, v is equal to a and b, and those two components are the components that I will use in the substitution through the function in order to get the directed derivative. I will use this law in case I'm not sure about the partial derivative existence of my function. I believe one example at least will make things much better. Those are the slides from Lipsman, exactly the same as I told you. This is the vector. It should be a unit vector, which means that the magnitude of the vector is equal to 1, or the norm of the vector is equal to 1. That's the simplification of what's happening, that we are finding the rate of a change of my function in the direction of u at certain point, which is x naught. All I have to do is to multiply the gradient vector of f at a and b times the components or the direction that I'm evaluating the directed derivative in its direction, which is u1 and u2, the components of this vector. Of course, once you do dot product, you will multiply the first component in the gradient vector in the first component in the vector, the second component in the gradient vector in the second component, and adding them together, as you can see. It's very, very simple, but the main issue is to memorize it. Once he asks you about the directional derivative, what I need you to have to know, or the training actually will make your life much easier if you solve these problems more than once and have the capability of just substituting and using the results, as you can see. This is exactly more the geometric interpretation of how to use the directed derivative and the tangent at certain point, blah, blah, blah. Once more, what's going to make everything more bright is having an example. So, for example, calculate the directed derivative of the function in x and y, which is 3x plus 2y squared at the point 2, 1 in the direction of the vector. So I need a function at a point and the vector that I'm going to use. The first step that I will have to do is to check if this vector is a unit vector or not. Please try to do this before continuing in finding your vector. So in order to do this, all I have to do is to get the sum of a square, the magnitude of the u vector, which is simply going to be the square root of the first component to the power of 2 plus the second component to the power of 2, and see if this value is equal to 1 or not. This is very, very simple to check. As I told you, we will normalize or check the direction vector. Step number 2, I will compute the gradient vector, which is very, very simple. Step number 3, you compute the directional derivative according to 0. So the first thing to do is to trying to check the value of u, which is a quarter to the power of 2 plus root 3 over 4 to the power of 2, which leads to a half. That means, which is not equal to 1, which means this is not a unit vector. How to bring a unit vector from any vector? Simply divide the components of this vector on its magnitude. So all I have to do is to divide the various components on the magnitude. So all I'm going to do is to divide 1 over 4 over 2, root 3 over 4 over 1 over 2 also, which means I will multiply the elements by 2 because you know denominator of denominator is denominator. So I'm dividing these values on half. So this value will be divided on 1 over 2. That value will be divided on 1 over 2, which leads to you will have 1 over 2 and root 3 over 2. Now, step number 1 is done. I've normalized my vector. Step number 2, I will need to evaluate the gradient vector. And the gradient vector for this function, if you get f sub x, it's gonna equal to 3. If you get sub f sub y, which is gonna equal to 4 of y. So now evaluating the gradient vector, I will replace the first component by 3, the second component by 4y, as you can see. I have the gradient vector also. The last step is to multiply both of them together. Before getting further, I will get the gradient vector at the indicated point, which is 2 and 1. So all I have to do is to substitute instead of y by 1, and if there exists x, I will replace it by 2. So it's a 3 times 4 or 3, 4. 3 and 4. Now I will write the formula of the directional derivative, which is the gradient vector of the function at 2 and 1 times the unit vector that I'm using, which is going to be 3 over 4 times 1 over 2 root 3 over 2, and you will have your value, as you can see, which is 3 over 2 plus 2 root 3. The topic is very, very simple. So at the time being, we already had two main things evaluated in this till the time being. How to get you advantage of using the implicit function theory, and how to evaluate the directional derivative, as you can see. It's really very simple. As I told you, that's the value of the directional derivative at 2 and 1 in the direction of a quarter and root 3 over 4. If you remember the analytic, the linear algebra and analytic geometry, we know that the angle between two vectors is very, very simple and it's connected to the dot multiplication. So we already know that the dot multiplication of u dot v is equal to the magnitude of the first vector times the magnitude of the second vector times cosine the angle between these two vectors, as you can see. So it's a magnitude of u times magnitude of v times cosine theta, as you can see. If u dot v is greater than 0, then your angle is going to be accurate. If u dot v is less than 0, then it's going to be greater than 90, okay, obtuse. And if u dot v is equal to 0, then you will have a right angle between these two vectors. Putting this in mind, it will help me to evaluate the maximum direction, which is simply, it's going to be the directed derivative, but the vector that I'm using is the normalization of the gradient vector of my function. So simply, I can find the directed derivative in this case, which is the maximum, equal to the gradient vector of f times, okay, the the vector that I'm using, which is the norm of f of the gradient vector at this point. So instead of having any vector, I will use the gradient vector as my vector. Type, if I want to get or to find in this case, of course, the angle between the angle will be 0 because it's a vector and itself. Type, if I want, as I told you, cosine theta will equal to 1, which leads to theta is equal to 0. It means they are identical, or they are coincide on each other. But the minimum direction of the directed derivative, it will happen when theta is equal to 180, and it will be the opposite direction of your vector. Okay, so once more, that's the some remarks about the gradient vector. If the gradient vector is not null, doesn't equal to 0, it is normal on the Riven curve of f passing through the point x naught y naught. That's a huge advantage of the gradient vector. Using the gradient vector at certain point, I can find the tangent plane at this point simply from this theory. So it's a very important remark to keep in mind. And the gradient vector also can be generalized on an open disk centered at X node, the gradient at G doesn't equal to 0, then it is the normal to the level surface of G at through this point. So simply, if this is applied, as I told you, and I want to get a tangent plane to your surface, all I have to do is to follow these steps. Step number 1, understand the setup. Step number 2, compute the gradient vector of F. Step number 3, use the tangent plane formula that you will see, which is really very simple. The gradient vector of F at X node, Y node, Z node times the position vector, which is X minus X node, Y minus Y node, Z minus Z node equal to 0. That's the equation of the tangent plane at certain point. If you expand it, it's gonna be X, partial F, partial X at X node times X minus X node, partial F, partial Y at Y node times Y minus Y node, as you can see in the explicit form of this, of the tangent plane. For example, if I want to determine the tangent plane of to this surface, which is an ellipsoid, at the indicated point, which is 1, 2, 1, all I have to do is to find first the gradient vector, getting the normal vector from the gradient vector by substituting at 1, 2, 1, then multiplying them together. I will solve it and then we will go through it together on the slide. So if I were in your shoe, all I have to do is to get the gradient vector of this function. So the gradient vector of F is simply going to be, see how easy it is. It's going to be a 2 of an X, 8 of a Y, and 2 of a Z. The normal vector, which is the value of the gradient vector at 1, 2, 1, is going to be really very simple. All I have to do is to substitute by 1, 2, 1, which is going to be 2, then 16, then 2, as you can see, that's the normal vector. Now I can find the equation of the plane, which is going to be the gradient vector of F at 2, 1, 2, dot product, the position vector X minus 1, Y minus 2, and Z minus 1, and this is equal to 0.